Hi folks, we're going to take a look at number 25 on page 270. So they want us to find all asymptotes, so horizontal, vertical, oblique, and any local extrema for these two functions. All right, so let's start with A. So first thing you should be looking at anytime you look at a rational function is there any simplifying to be done? And we see that there is none. In fact, even in the second one, no simplifying. So now we can go ahead and use our algorithm for determining all the characteristics. So in particular, vertical asymptotes, once it's in simplified form, occur anytime the denominator is equal to 0. Okay, so our vertical asymptotes, and here we don't really need to solve. We can see clearly that it's going to be x equals 3 and x equals -3 are two vertical asymptotes. Don't forget to give them in the form of an equation since they're lines. All right, so next thing is to see if they have any horizontal asymptotes, or might it have an oblique asymptote? In other words, what's going to define the end behavior of this function? So here we just have to look at the degrees of numerator and denominator, and I see that the denominator has a higher degree than the numerator, so it automatically has a horizontal asymptote of y equals 0. All right, so if I asked you to explain that, you'd have to specify that degree of the denominator is larger than that of the numerator. Okay, we can identify that that's going to be the end behavior, y equals 0. So since there's a horizontal asymptote, there won't be any oblique asymptotes. So let's now go to finding the critical points in order to determine any local extrema. And of course, we do that by finding the zeros of the derivative. So let's start by finding the derivative here. So I'm going to consider this as the derivative of 8 times x squared minus 9 to the -1. Okay, use the chain rule instead of the quotient rule. So here, bring down the -1. So I'm going to have -8 times x squared minus 9 to the -2. And then I have to apply the chain rule. So I have to now take the derivative of x squared minus 9, which is 2x. All right, so when we clean this up, what do we end up with? We end up with -16x over x squared minus 9 squared, and of course we want to determine when this is equal to 0, and since it's a fraction, this only occurs when the numerator is 0, and so x equals 0 is our only critical point. All right, so since they want us to find the local extrema, let's actually find the y value. Actually, first we have to determine if it's a max or min. Okay, so we do that by testing the sign of y prime on either side of 0. So I notice that the denominator is always positive, so I only have to look at the numerator here. So let me pick -1 and 1. So when I stick in -16 times -1, I'm going to get a positive value, and -16 times +1, I'm going to get a negative value. So this is going from increasing to decreasing. In other words, this is going to be a local max. All right, so in order to find the y value, well, we find y at 0, which is equal to, so let's just stick x equals 0 in here, and so we just have 8 over -9, so -8 over 9. All right, so the local extremum occurs at, so here it's a local max at 0, -8 over 9. All right, so let's move on to the next one. So here, again, this is already in simplified form, so our vertical asymptotes are nice and easy. We just have to determine where the denominator is equal to 0, and that happens at 1 and -1. So our vertical asymptotes are x equals 1 and x equals -1. All right. Now for the end behavior, in other words, to see if there's a horizontal or oblique asymptote, we again look at the degrees of numerator and denominator, and I see that the numerator now has the larger degree. So that means that this function is approaching positive or negative infinity, but because it's 1 greater than the denominator, we know there's going to be an oblique asymptote. Okay, so let's determine the oblique asymptote, which we do by dividing, by finding the quotient of these two functions. So since I'm not dividing by a linear divisor, I can't use synthetic division. If I was dividing by a linear, I'd be using synthetic division. So here I will have to use long division. All right, so recall that I have to add in any terms that are missing. So here this is going to be 4x cubed plus 0x squared plus 0x plus 0 divided by, and here there's missing the x term, so this is going to be x squared minus 0x or plus 0x minus 1. All right, so I need to eliminate the 4x cubed, so I'm going to multiply that by 4x. So place it above here. So 4x times x squared is 4x cubed, which I'd like. 4x times 0x is just 0x squared, and 4x times negative 1 is negative 4x. And then, of course, we subtract these. So these disappear as I wanted to. 0x squared minus 0x squared, there's nothing there. So 0 plus 4. So I'm left with 4x. Okay, but that's as far as I can go. Since I don't have any x squared terms, there's my quotient. I'm not interested in the remainder term, so I'm just interested in this quotient. So our oblique asymptote is just y equals 4x. All right. So let's now look for the local extrema, see if there's any. So again, I'm going to start by finding the derivative. And here, of course, I'm going to have to use the quotient rule. Okay, so it's the derivative of the numerator. So 4 times x cubed, derivative is going to be 3 times 4, 12x squared, times the denominator function, x squared minus 1, okay, minus the numerator function, 4x cubed, times the derivative of the denominator function, which is just 2x, and all over the denominator squared. Okay, and of course I want to determine where this is equal to 0, but I'm going to want to simplify what's going on in the numerator here. So we're left with 12x to the 4th minus 12x squared, and this is going to be minus 8x to the 4th. All right. Now, since I'm looking for this being equal to 0, I can just multiply this term to the other side. It'll just be 0, so I'm just interested in when the numerator is equal to 0. So 0 is equal to, so this is going to be 4x to the 4 minus 12x squared. So let's factor this. Take out a 4x squared, so I'm left with x squared minus 3. All right, so now that I have in factored form, what's going to make this 0? Well, x equals 0, and what's going to make this here? Well, x can also be equal to plus or minus square root of 3. All right, so I've got 3 critical points. Now let's test our intervals to see if there's a sign change and what that sign change is. So we've got negative root 3, we've got 0, and we've got root 3. So take something less than this. So take negative 2. We've got negative 1 in between here. We've got 1, and we've got 2. Okay. Now remember, when I look at my derivative, that denominator was squared. So that denominator is always positive. So I only need to focus on the numerator, and I'll use the simplified form of the numerator. Okay. So 4x squared is always positive. So I only need to look at the term inside the bracket. So you see, by going through that process of figuring out that denominator is positive, don't need to think about it. Might as well work with factored form and realize that the 4x squared is always positive. Don't need to think about it. It makes determining these signs much easier. I just have to look at this x squared minus 3. So negative 2 squared is 4, minus 3 is 1, so positive. Okay, negative 1 squared is 1 minus 3, so that's negative. Okay, 1 squared is 1 minus 3. That's also negative. And then 2 squared, 4 minus 3 is positive. So I see here at 0, I do not have a local extrema. So no extrema here. Okay, but at negative root 3 and positive root 3, I do have extrema. So here, since I'm going from positive to negative, this is going to be a max. And since here I'm going from negative to positive, this is going to be a min. All right, so we just have to determine our y values here. So we have a local max at negative root 3. So let's stick negative root 3 now into our original equation. I kind of don't really want to do this, but I guess let's, what do we have? Okay. If I was graphing this, I would be finding an approximation, but I guess here I should go ahead and actually find these y values. So I'm just going to write this at the bottom. Y equals 4x cubed over x squared minus 1. Okay, just a reminder. So here, if I'm looking for y at negative root 3, all right. So let's see what this gives me. This gives me 4 times negative root 3 cubed over negative root 3 squared is 3 minus 1 is 2. Okay, so this part I have negative 2 times, and this is going to be, I'm just going to rewrite this instead of square root of 3 cubed, I can bring the cube inside the square root. Okay, so this is just going to be 2 times the square root of 27. Okay, because remember here I have 3 to the 1/2 cubed is the same as 3 cubed to the 1/2. Okay, just using my exponent rules. All right, so here we've got negative 2 root 27. Okay, and now let's find our local min. Local min occurs at, so positive root 3. Okay, and when I put this into my equation, y at root 3, well, I'm going to get something very similar. So I'm just going to get 4 times root 3 cubed over, again, root 3 squared is 3 minus 1 is 2. So again, I'm just left with positive 2 times, and this is going to be square root of 3 cubed is 27. So this is going to be positive 2 times square root of 27. Okay, that didn't end up being as bad as I thought it was going to be. But again, if I was just graphing these, I would have definitely just found approximations. But since they actually just asked for the local extrema, I should be giving exact answers. All right, so let's take a recap of these here. So these were both rational functions. So step number 1 was to check that they're in simplified form. Okay, once they are, vertical asymptotes are whatever makes the denominator 0. Horizontal asymptotes, oblique asymptotes, in other words, end behavior is determined by comparing the degrees of each polynomial. In this case here, numerator larger degree, so automatically y equals 0. Here, numerator larger degree of 1 more, so we needed to find our oblique asymptote by dividing. Okay, and then of course finding local extrema is about finding the zeros of the derivatives and then testing the intervals on either side for the derivative signs. All right, that's it for this one.